let's go. So here's assignment 2-3. So I think in the other videos there's always a little bar on top, so I thought maybe I'll clean it up a bit, make it look prettier. Here's work on rational functions that everyone needs work on. So this is not a calculus lesson, but this is a good pre-calculus lesson that you need. So f of x equals x over x squared plus 1. And the question is just domain and end behavior. So first, when I look at the domain, I'm looking for any value for x that would make the denominator 0. So if you like, you can always take the denominator, make it equal to 0, and then solve it to find what those x values are. Now, when I try to solve this, so when you subtract 1, and you notice x squared can never equal -1. Or if you square root, you get an imaginary answer. That means, in this case, the domain is all real numbers. There are no restrictions. So even though we have a fraction, you can have a continuous function if the denominator doesn't have a 0. So there's no 0 in the denominator. It's imaginary, so it's continuous. How about the end behavior? So if I want to know the left end behavior or the right, I'm going to do a limit, and I'm going to see the power over power. So x over x squared plus 1. So how am I going to find the left end behavior? With power. Notice the bottom is more powerful. It's 0. It's over at that point. Same thing with here. If I want the right end behavior, same answer. That's the horizontal asymptote. So if the bottom is more powerful, then the end behavior for both ends is 0. Number 2. Number 2 is f of x equals x minus 1 cubed, and then x squared, x minus 1. And then this one asks something a little different. It says domain, whole, and vertical asymptote. So first of all, the domain. So for the domain here, I'm going to write it like this, where x is an element of all real numbers. There are two values x cannot be. So if I look at x squared, and again, if you like, you can take that factor equal to 0. You can square root 0. So one answer that x cannot be is 0. And the other one, x subtract 1 equal to 0 and solve it, would be positive 1. Again, if you plug in 0 and multiply, it's 0. If you plug in 1 and then subtract and multiply, it gives you the answer 0 in the denominator. Both are domain restrictions. The second question was whole. Is there anything removable here that would create a whole? And it's removable in the denominator. And I want you to notice that you can simplify this. So I'm going to do that. That x goes into x squared, and you're left with an x in the denominator. X minus 1 cubed simplifies with x minus 1, but you're left with x minus 1 squared in the numerator. So subtract the exponents to see that. I'm interested about what got removed from the denominator. So notice x remains. So where would the whole be is where it got removed. So what got removed was x minus 1. So this discontinuity is positive 1, and the y coordinate, then I would plug back in to find it. So if I plug in 1 here, 1 take away 1, that's 0 divided by 1, which is 0. So there's a whole at 1, 0, and the other would create a vertical asymptote. So then it says, where's the vertical asymptote? And so when x equals 0 is a vertical asymptote. When x equals 1, there's a hole. So this created a hole. This created a vertical asymptote. Removable, non-removable. And again, we're looking at, is in the denominator, can you remove it? Is it removed from the bottom of the fraction? It can stay on top. Number 3, f of x equals negative x square root of x squared minus 1. So domain and all horizontal asymptotes. So make sure I know what we're talking about. So when I look at the domain, I'm looking at the square root of x squared minus 1. That's what I'm looking for. So first of all, I'm trying to get a sense of, I can't have this to be negative. So this answer has to be greater than or equal to 0. It can't be negative. In fact, it can't even be 0. Because if it's 0, it would also, even though you can take the square root of 0, that leaves you with a 0 on the bottom, which is bad. So it can't even be equal, just greater than. So I'm going to factor it for me to see it just a little bit better. So what values would make this positive, in other words? So if I plug in a number, and then if I look at it, I'm going to create a little number line so I can understand it better. So if I create a number line, what are the zeros here? So we have one at -1 and one at +1. And then I want to know in each interval what happens. So if I plug in a number bigger than 1, do I get a positive answer? Yes. If I plug in a number between -1 and +1, what kind of answer do I get? So what's an obvious number between -1 and +1? That'd be 0. So, or you could plug in any number in between, but 0 is the easiest. If you plug in 0, you get -1 times 1, which is negative. So you can't put in an answer between -1 and 1 because it gives you a negative answer. If you plug in an answer smaller than -1, like -2, so if you plugged in -2 and look at both, notice you have a negative times a negative. Well, a negative times a negative is positive. So when I look at the domain here, in terms of what I'm looking for, I'm looking at where it's positive. So let's look carefully so I can write it. So if I write this, I can write it, it goes from -infinity to -1, but does not include -1 because plugging in -1 makes it 0. And this is a fancy word in math for and. It means union. So -infinity to -1, and we are doing and +1 to infinity. Notice I'm using round parentheses to know that it can't be equal to that. So the domain goes from -infinity to -1 and +1 to infinity. In between -1 and 1, it is imaginary. So there's a break in the graph there. What was the other part? Horizontal asymptotes. So the horizontal asymptotes come from power over power. And so when I look at this, it's -x. And then when I take the square root of x squared, it's going to be positive and -x. So when I look at it, there's positive and -1, or horizontal asymptotes. So believe it or not, to the right, the end behavior is -1, and to the left, it's +1. Because a negative divided by a positive gives you that negative, and a negative divided by the negative gives you that positive. So there are two horizontal asymptotes, +1 and -1. All right, number 4. Now we're going to be graphing. So I'm going to try to do the analysis on the left and do the graph on the right. So for number 4, you have f at x equals x plus 2, x subtract 1 squared. This is a polynomial. So it says for each graph it without a calculator. We're sketching it. We're just trying to find the important parts here. So clearly I think the x-intercepts are important. So what makes the x-intercepts here? It's not irrational. So this is a polynomial. There's no fractions. There's no vertical asymptotes, holes, none of that. Just smooth and continuous. So notice at -2, there's a hole. What's the exponent, odd or even? And because it's an odd exponent, it's going to cross at -2. At +1 is another one, and because of the even exponent, it's going to touch. So I'm just going to sketch this. So I'm going to find -2 and +1. Do I know the end behavior here? Well, if I multiply it out, the power term is x times x squared. So just the most powerful term with no parentheses is x cubed. So because it's positive with an odd exponent, I know the right end goes up and the left end goes down. If I want to find the y-intercept, I can plug in 0. So if I plug in 0, I get 2 times 1. -1 squared is 1, so 2 times 1, so I get 2. So I already have this part of the graph. Now I'm going to plug in one more number. So I'm going to plug in -1 and see if that gives me a turning point, just an estimate turning point. In calculus, you're soon going to find that we can find that turning point exactly without a calculator. All right, -1 plus 2, that's 1. -1 and -1, that's -2 squared. So this is 4 times 1, which is 4. So at -1, we're going to go to 4. And then this is smooth and continuous. And you just sketch that function without a calculator. But just for fun, we are going to go to Desmos. And when you go to Desmos, does it match what I just did? That was x plus 2. That's x subtract 1 squared. So, look. Yes, yes, yes. Even this one, it's perfect. And we did it without a calculator. But we were going to check at the end and make sure we did it right. All right, number 5. In number 5, you have f at x equals x to the 4th minus x squared. So this is a polynomial. So the domain is all real numbers. The first thing I'm going to do is factor out an x squared. That leaves me with x squared minus 1. And then if I continue, that's a difference of squares. Now it's completely factored. I want to see where the x-intercepts are. And I want to know the power term. So we have an x-intercept at 0, and it only touches at 0 because of the even exponent. Then at positive and negative 1, we have zeros, but they're odd exponents, so at positive and negative 1, they cross. So let me just draw a little graph here to represent that. So I'm going to let that be 1 and let that be negative 1. And then let this be 0. So we have our zeros there. What do we know about the power term? There's no parentheses here. So the term with the biggest exponent, it's x to the 4th. What does that tell me? The right end and the left end go up for x to the 4th because it's positive with an even exponent. And then what's happening? Well, at positive and negative 1, it crosses. Now, if I plug in a number like 1/2 or 1/3 into here, I'm not going to do it, but it's going to create a small answer. Same with negative, because you're taking the power of a fraction, a number smaller than 1, it's just going to get tiny. So I'm not going to do the work to evaluate it. I can do a calculator to do that. I'm just sketching it. So I know it crosses, but it just crosses a little bit. And then at 0, it's going to touch and not cross over because of the even exponent. And again, it's just going to be a little dip here, right? And then it continues through. So there's my little sketch with end behavior and intercepts. If I see if I did it correctly here, I'm going to type it in, x to the 4th, subtract x squared. And if you look here, you can tell it's exactly the same. And notice that if I wanted to, the turning points are negative 1/4 and negative 1/4. So it just did what I said. It barely dipped below the axes and then touched and then came back up again. Perfect. All right, let's continue. Number 6. All right, here we have a rational function. So that fraction where we have a variable in the denominator, we have more things to look at. Now, we can still look at the domain. Know that x, what can x not equal? Look at the denominator, it's negative 2. It's non-removable, right? So that means at x equals negative 2 is a vertical asymptote. The x-intercept comes from on top. What makes the top 0? That's positive 2. And we can start from there. Maybe the y-intercept gives us one more point. Plug in 0, and you get negative 2 divided by 2. So there's a y-intercept at negative 1. All right, let's graph this together. So what things am I looking at? Well, at negative 2, I said there was a vertical asymptote. Oh, there's one thing for sure I didn't find, and I'll come back and find it. At positive 2 and at negative 1. Now, one thing I didn't find, of course, was the horizontal asymptote. So that gives me the end behavior. And I know it's horizontal because the powers are the same. So if I go power term over power term, that's x divided by x. That gives me the horizontal asymptote of 1. So at 1, we have a horizontal asymptote. Now, the behavior of this is that the right end behavior is going to get closer and closer to 1. And then you can see this curve that it's going to go to negative infinity to the right of the asymptote. And because I recognize that this is an odd vertical asymptote, it has an exponent of 1, this up here then must go in the opposite direction, but yet it must curve and have the end behavior still of 1. So I understand my curve, I understand my end behavior, I understand the behavior at the vertical asymptotes, I understand the intercepts, I put it together and I'm done. So I have the ability to sketch something. I could be more detailed, but I just want the ability to sketch and understand the function and what it should look like. Number 7. Another rational. So that's x plus 2 squared, x minus 4, x minus 1 squared. So the first thing I look at when I look at this, is there anything removable here for a whole? And there isn't. So the domain comes from the denominator. I can see that x can't equal positive 1. There's nothing that removes it, so that is a vertical asymptote. And it's important to know that it's even with an even exponent. That means on both sides it's going to go in the same direction. So at a vertical asymptote, it's either going to go to infinity or negative infinity. When it's an even exponent in the denominator, they both are going to go up or both go down at that vertical asymptote. All right, what else should I know? The numerator, x-intercepts, I see it at negative 2 with an even exponent, so it's going to touch. I see it at positive 4 with an odd exponent, so it's going to cross. And I'm not going to forget this one. There's a horizontal, is there? Or is there not a horizontal? I think there's an oblique. So if I look at the power here in terms of the end behavior, maybe I should do this, write it as a limit. Notice the power terms here. If I look at it, it is x squared times x. That's x cubed. And in the denominator is x squared. So if I simplify it, the power term is x. That means this is going up to the right and down to the left. That's the end behavior. The right end behavior is infinity, and the left end behavior is negative infinity. So let's see what we got here when we graph this. And see, again, I'm looking for a sketch. It's not going to be perfect necessarily where every point, but enough points where I can see the behavior of what's happening. So what do I know so far? So at negative 2 and 4, I know there's an asymptote at 1. I know it's going to go up to the right and down to the left. So let's just get a sense of what's happening here first. So because it's going up to the right, I know it's going to, at positive 4, it's going to cross. So it's up to the right and then it crosses. And I know the behavior at the vertical asymptote is either goes to negative or positive infinity. So if it's crossing, it's going to negative. I also know this, that on the other side, it's going in the same direction. That's that even vertical asymptote. Now maybe a y-intercept could be helpful here. So if I plug in 0, I get 4 negative, I get negative 16. I can even like put that like on the graph. So somewhere down here, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Let's just pretend and count by 4s. Why not, right? Because it's my graph. Negative 4, negative 8, negative 12. Let's pretend that's negative 16. So we have a y-intercept of negative 16. So I just plugged in 0 for x and simplified it. That it's going to, both sides are going to go to negative infinity. Remember here it's going to touch. And then when it touches, the left end is going to go down. So there's my sketch. Kind of weird and awkward a bit, right? But interesting. It crosses, it touches, the behavior at the asymptote. Can we see the graph of Desmos to see if I led you astray or if it's accurate? So here, let's get rid of this. Oh, I didn't even do the other one, which was x minus 2 over x plus 2. We didn't double check that one. But if you can see that one from before, it does match. So if you look back, you can see that this one matches. This one's more interesting. So it is x plus 2 squared, x subtract 4, and in the denominator is x subtract 1 squared. And then I'll minimize this so you can see it better. Does this match my graph? So can you see at 4 what it does, and at negative 2 what it does, and that there's an asymptote at 1, and you can see the behavior of the graph and what my behavior was. So back here, there's a great sketch of what happened even without a calculator. All right, number 8. F at x equals x squared plus 1 over x. Let's do that. So what things am I looking at? X squared plus 1, not factorable. That is x. So if I take the numerator equal to 0 and try to solve it, what I realize is that there is no x-intercept. So it would be imaginary, right? But there is a y-intercept. So if I plug in 0, I'm left with, actually if I plug in 0, that means also, right? Doesn't exist. So there is no y-intercept. So there are no intercepts here. Are there any asymptotes? Well, the domain restriction here, x can't equal 0, it's non-removable. So that 0 creates a vertical asymptote. There's no holes because nothing's removable. How about the horizontal asymptote? So power over power, x squared over x, there is no horizontal asymptote. So instead, the end behavior is y equals x. That's what gives you your end behavior. So that's x squared divided by x. That means it's going up to the right and down to the left. There's my end behavior. So let's sketch this. So we have no intercepts. So we do need a point of some sort, at least to start with. We do have a vertical asymptote at 0. But we don't have a horizontal at all. So if I plug in 1, I get the answer 2. So that's at least something to curve through. For the negative side, if I plug in negative 1, I get negative 2. So believe it or not, that gives me a sense that it has, it's an odd function, that it has symmetry with the origin. So no, here it's going to infinity. Here it's going to go to negative infinity because it's an odd asymptote. And no, I don't know where the turning point is exactly, but I do know that this is going to go up, and I do know this is going to go down wherever that turning point is without touching the axes. So there's my sketch. So let's see how accurate I am in terms of that. So let's look at it. So that is x squared plus 1 over x. Oops, what the hey did I do? Let's use parentheses there, I guess. So x squared plus 1 over x. So I'll just zoom in here. You can see a little bit here. See how it's the same picture? Now that turning point happened to be at 1, 2. Yay, I did it right. Negative 1, negative 2. I actually didn't know where it turned. I just estimated where the graph would turn. It was going to turn about there. What I cared about was the end behavior. Notice the right end is going up, the left end is going down. What's the behavior at the vertical asymptote? So I focused on those big ideas and just sketched around those big ideas. All right, number 9. Oh, C problem 1. So this is the one. We just did number 9, didn't we? Did we do number 9? No, I did x squared plus 1 over x. So this is x over x squared plus 1. Now, in number 9, we did some of this work. It's a continuous function. We said that there's a horizontal asymptote at y equals 0 because the bottom is more powerful. There is no vertical asymptotes and there's no holes because it is continuous. So what is this going to look like then? All we have is this to begin with. So let's draw this. So we do have a horizontal asymptote for the end behavior. what happens for intercepts? So we do have a x-intercept. So plug in there, it's 0. And if I plug in 0, it's also a y-intercept. So we have that. But what's happening to the right and what's happening to the left? So if I plug in positive 1, I get a half, positive 2, and so on. So it goes up slightly, but then it comes back down. What's happening here, if I plug in negative, it's going to cross, because it's going to give you the answer negative a half, and then the fractions are going to get closer and closer here. So it crosses at 0. It is barely above the axes on both sides with that end behavior. So let's just look to see what that looks like. So this one is x over x squared plus 1. So again, this one actually goes as low as negative a half in terms of, so what your scale is. But notice that it goes, it crosses at 0, but the end behavior on both sides is 0. Also notice it's continuous. So when you look at it, there is no holes, no breaks, no jumps. It's a continuous, even though it was a fraction with variables in the denominator. All right, number 10. In number 10, you have f at x equals. You have x subtract 1 cubed. In the denominator, you have x squared, x minus 1. And this one is just like problem 2, which we did before. So in problem 2, what did we already find in problem 2? As I go back here, well, we found that there was, back to problem 2, that there was a vertical asymptote at x equals 0, that there was a hole at 1, 0. I'm just going back to question number 2, because it's the same question. We're just going to graph it now. We didn't find any intercepts. So when we simplified this, we got x minus 1 squared over x. That's what it looked like when we simplified it. So there is an x-intercept at positive 1, but actually there's no x-intercept because at positive 1 there's a hole, and there's a vertical asymptote at 0. So let's just see how far we get here. If we need to add some things for my sketch, then that's what I'll do. So here's my sketch of that function. I know there's a hole at 1, 0. I know at x equals 0, there's an asymptote. That's right over the y-axis. Horizontal, there is not a horizontal asymptote. If I look at the power terms, that's x squared over x. That simplifies to x. So it goes up to the right and down to the left. So from this hole, by the way, this hole, which comes from here, it's going to touch. So it has an even exponent right there, the hole, which means I know the right end goes up and then it touches and then it goes to positive infinity. Here, the other end is going to go to negative infinity, and I know the end behavior. So somewhere here it's going to turn and then go that way. So there's my sketch of what it looks like. Let's look here. So let's erase this. So we have x subtract 1 cubed. In the denominator, we have x squared, x subtract 1. So x squared, x subtract 1. So that's what we have. So look here in terms of what we have. So notice here you have a hole. So there you have a hole, but it just touches at that hole. So notice it has that even multiplicity with that even exponent, so it doesn't cross over. At the vertical asymptote, it goes up to infinity, and then on the other side, it goes in the opposite direction. And notice the end behavior here. So if I look at the end behavior, the right and the left end, in fact, if you really zoom out, you can actually just see a line eventually, right? So I said it makes a line, right, the power terms. So if you put in big enough numbers, eventually all you would see here is a line, and then what happening at the asymptote. So there's that line that I see. Pretty interesting, I think. All right. what number are we at? Number 11. So at number 11 we have f at x, oh this is lengthy, x minus 1 squared, x squared plus 1, x squared minus 1. So right away I'm going to write that as x plus 1, x minus 1. So the denominator is difference of squares. Now I'm just going to analyze it quick before I do anything else. So first of all, is there anything that simplifies here that may remove the denominator to create a whole? So x minus 1 and x minus 1. That removes the x subtract 1 from the denominator. So that means at positive 1 there's a whole. See how I remove this? So I know, because of the removal, that at positive 1 there's a whole. If I plug positive 1 into here, 1 take away 1, you can see the answer is 0. So at 1, 0, there's a whole. Vertical asymptote, that's what was non-removable. So look at the denominator, and it's negative 1, and it's odd. So it's going to go up in one direction, down in the other, because it has an odd exponent. The power terms. So if I look at the power terms here on the top and bottom, I can look at the reduced form. That's x cubed over x, or x squared. That means that when you reduce it down, both ends, the end behavior is going to follow the end behavior of a parabola. That means the right end and the left end both are going to infinity. So we're going to take that, what we know, and we're going to sketch it. And if I want to know more, then I'll find more if I need it. So do you have the ability to sketch these? So we have a whole at 1, 0. We have no x-intercept, by the way. So at 1, 0 is a whole. X squared plus 1, make it equal to 0. It's imaginary. So there's no other x-intercept. The y-intercept, if I plugged in 0 for x, would leave me with negative 1 divided by 1, which is negative 1. So we do have one there at negative 1, the y-intercept. We have a vertical asymptote at negative 1. And we don't have a horizontal. So let's just see what we have so far. Oh, my disk is almost full, so I better stop here soon. So to the right, it's going to cross at that hole. Notice that it has an odd exponent right there. So it's going to cross at that hole. It's going to go up. And at the vertical asymptote, it goes to negative infinity. On the other side, it goes in the opposite direction. And somewhere here, it's going to turn and then come back up because both ends are going up like that parabola. So that's my attempt at sketching this. And I'm not even pretending to try to find where it turns. I just know it does turn and it doesn't touch or cross the x-axis. So let's look at this, and then I'll do a second video where I delete some memory so I have memory to do a second video. But let's finish this off. So what was it again? So that equation was x subtract 1, oops, try it again, x subtract 1 squared, x squared plus 1, and then x squared subtract 1. So make sure I typed it in correctly. There it is. I'm going to press the home button so it centers it again. So let me just make sure that we can understand what's happening here. So here, there's a hole. Oops. So there's the, cancel that. All right, here's the y-intercept. If I follow along here, notice that there's a hole at positive 1, but we crossed it. Now in my graph, I kind of flattened it. So by looking off of Desmos, I can see it goes up pretty quick. So I should adjust that looking off the graph, that it rises very quickly and not slowly. But look here, I didn't know where the turning point was, but I did know that this goes to infinity, it turns, and then that also must go to infinity, that both the right and the left go up forever. So what's the end behavior? What's the behavior at the intercepts, at the vertical asymptote? Is that accurate? And using intercepts or maybe other points to try to tie it together. So the only thing I would adjust for my sketch is It doesn't increase slowly. So instead, it increases very fast. So it's concave up as it goes there and not concave down. So here it is. We have a hole, and you can see the behavior at the vertical asymptote, the end behavior, and whatever else I need just to get a sketch of what's happening. All right, Mr. G Math over and out. Until I got memory to do another video. Till next time.